All right, so with the previous video, we were looking at the ionic compounds. So that's where we actually have a transfer of electrons. Typically, a metal is going to lose electrons, a non-metal is going to gain it, and then the atoms become a positive and negative ion, so the cation and the anion, and then the opposite charges are what bring those together. But when we've got two nonmetals, that's going to be where we see the covalent bonds. And in this case, what's actually happening is the electrons are being shared between those two atoms. So instead of one atom essentially taking the electrons from the other, in this case, it's going to be more balanced. We'll see when we get to the end of this first quarter, beginning of the second quarter, we'll see that it's not a perfect sharing always. In some cases, it may be. So we still might wind up with a slightly negative or a slightly positive charge. But it's not going to be a fully positive. It's not going to be a fully negative charge like we see with the ionic substances. And with it, we're going to be primarily focused on covalent compounds. And remember, you can even see it here. I call them covalent just because the bonds themselves are covalent bonds. Some sources, like the textbooks, refers to them as molecular compounds. Those two terms are synonymous. So just know if you do see one or the other, they mean the same thing. But we're going to be primarily focused on binary covalent compounds. So just where we have two elements together. So if you think about binary code, for instance, it's just zeros and ones. Those are the only two options. That's what we're going to be looking at with these types of compounds. And you can see a few of them here. So when you're looking at these ones, if you look at the formulas we have here, look at the names, you can see we've got prefixes. So you've got like dioxide, trioxide, tetroxide, pentoxide. It's going to be the same prefixes as the hydrates from that little ionic section of the chapter. So again, you don't have to memorize those. Some of them you're already probably familiar with. Some of them, like tetra, hexa, hepta, deca, maybe a little bit less familiar. But see if you can just look at the names we have here, along with their corresponding formulas. Think about like carbon monoxide and carbon dioxide. If I told you that water, so H2O, could be referred to as dihydrogen monoxide, think about kind of if we were to create a set of rules for these compounds in terms of naming them, think about what those rules would be. And then also with it, just thinking about dihydrogen monoxide. One reason that it's important to be kind of scientifically literate, understanding what that terminology represents, is because there's a video, I forget who it is, but if you just search like dihydrogen monoxide petition, you'll find there's probably a couple videos, but there's one video in particular where a woman has a petition and she's at like a county fair or something. I don't know where she was actually at. But she's got a petition to ban dihydrogen monoxide just because it sounds like a scary chemical name. And then she goes on to tell people that it's in our water supply. It contaminates our food that we grow. Excessive consumption can kill you, and a few other things to make it kind of sound scary. But it's just referring to water. We could also call water hydrogen hydroxide. So there's a few different ways that we can kind of refer to different substances. So it's good that we have an understanding of kind of what those represent, because some of them, like we see here, do sound like kind of traditional chemicals. But everything in the world around us is chemicals. Everything is made up of atoms. Everything's made up of compounds and things like that. So it's good that we have an understanding of what those things are. But if we think about the rules we could put here, if we wanted to actually name these compounds, if we think about carbon monoxide versus carbon dioxide, if we think about the examples we have here, what we're going to have is, so again, binary covalent compounds. If we had larger covalent compounds, there'd be different rules. So if we had multiple elements, there'd be a different nomenclature we'd have to use. But if we're thinking about simply naming binary covalent compounds, the second element has the ending changed to IDE, and we always use a prefix. So we always have to specify with that second element exactly how many there are. So if you think about, again, carbon monoxide, carbon dioxide, that oxygen, we have to specify. And that's also, I should mention, why we have these prefixes to begin with. Unlike the ionic compounds, where we have set charges, and they can only combine in a specific ratio. Again, sometimes with the transition metals, with the multiple charges, we can have different ratios. That's why we have to specify the exact version of that metal. But with these ones, we're going to see they can form single bonds, double bonds, triple bonds, so they can share those electrons differently, which is why we're allowed to have those different ratios. So again, carbon monoxide, carbon dioxide, 1 in 1 or 1 in 2. You can see a couple of the nitrogen oxide compounds. So if we simply refer to these as like nitrogen oxide or sulfur oxide, that would tell us what elements we have, but we don't know the actual compound we have because we can have them in differing ratios. So with the second element in the formula, we're always going to change that to just IDE for the ending, and then we'll always slap on a prefix there to tell us exactly how many there are. And for the first element, we can keep the name as it is. And then I'll put, oops, let me just do this. Let's just make this a little neater. With the second element, we can keep that name just as it is. So oxygen or nitrogen, if we look at NO2, nitrogen. So we're just going to keep that as it is. And then we'll do, but we need a prefix if there's more than one. So if you look at these ones, sulfur dioxide, sulfur trioxide, nitrogen dioxide, sulfur hexafluoride, boron trichloride, all of the, and even phosphorus pentachloride, all of those just have a single atom of that first element. Same thing with carbon monoxide, carbon dioxide. So with that first element, if there's just one of them, we don't have to add a prefix. We don't have to specify like monocarbon dioxide or monosulfur trioxide. So with that first element without a prefix is just assumed to be one. But then if we do have multiple, that's where we actually need to specify. So that's why we have dinitrogen tetroxide, dinitrogen pentoxide, tetraphosphorus decoxide. And actually, I believe this name is actually slightly incorrect. So typically when the prefix itself ends in an A, and then that element, like oxygen, typically we would just get rid of the A and call it decoxide rather than decaoxide. Same thing if it was like hexoxide. Do we have any example of that here? But again, with these prefixes, you don't have to memorize them. We just have to know how to use them. So that's going to be always with the second element in a covalent compound, and then only with the first one if we have more than one. So if we look at these ones, if you want to take a moment and just kind of go through them on your own, you can. I'll just do this actually. So we'll do send this to the back. So then I'll take this and just. All right, so for A, if we're looking at it, actually I can just do the letters. So for A, we've got sulfur and we've got fluorine. So we can just list those elements to begin with. But remember, we want to change the ending of the second one, so we'll have sulfur fluoride. But in order to get the perfect formula, we need to specify how many of those we're going to have. So we'd have sulfur hexafluoride. But with the second one, same idea. Write out what those elements are. Nitrogen oxide, or nitrogen oxygen, I should say, which will become nitrogen oxide. So if you ever hear of NOx compounds, NO and then little x, NOx compounds are just going to be nitrogen oxide, but it's just going to be kind of any ratio. So those are sometimes environmentally important. They have implications in terms of acid rain. And then when I was in Utah, they affected the air quality as well. But if we want to specify, we have N2O3 in particular. We always need that prefix on the second element, so we have trioxide. But in this case, we've got multiple of the first one as well, so we just have dinitrogen trioxide. See, we'll have chlorine, oxygen, which will then become just oxide. And again, we've got multiple of that first one. We've got two of them again, so we'll just have dichlorine. And then with the prefix for 7, you may be unfamiliar with this one, but if you think about a hexagon, or not a hexagon, a heptagon, it's a 7-sided shape. So the prefix for 7 will just be hepta. But like I was saying, with the oxygen, when we've got the prefix ending in an A, and then we've got oxygen, we're just going to get rid of that A. So heptoxide rather than heptoxide. And then for the last one here, phosphorus, and then oxide once again. In this case, we've got hexa, but it's still that scenario where we've got the A, so we'll just have hexoxide. And then we'll have tetra. So tetrahedral is going to be something that we'll talk about quite a bit when we actually look at the structure of these types of compounds in the beginning of the second quarter. But a tetrahedral is just going to be a 4-sided shape. And that's why we're going to have 4 of these phosphorus here. Okay, that's just what we had. So with these ones, if we want to go in the reverse direction, we can do kind of the same thing. In this case, I think it's a little bit easier than with the ionic compounds, because with the ionic compounds, we've got to kind of identify what the charges are and think about the ratio that those are going to combine in. In this case, though, the name tells us what elements we have, tells us how many of them we're going to have. So for the first one, we're going to have phosphorus and then chlorine. And then since it's just phosphorus, we're only going to have one of those. So I'm just going to do that there so the subscript doesn't get put down. But then with the pentachloride, that means we're going to have 5 of those chlorines. Dinitrogen monoxide, so we've got nitrogen and oxygen. And then with monoxide, we don't need any of the subscripts there because it's just assumed to be 1 unless we include a specific number. But we've got dinitrogen, so we've got 2 of those nitrogens down. We've got N2O. Want to make sure we include that so we're representing the correct formula. Iodine heptafluoride means we've only got a single iodine because it didn't specify otherwise. And then for the heptafluoride, we're going to have 7 of those fluorines. Whoops, 78. So we would just want to make sure we include that as well. And then with the final one, carbon tetrachloride. So if you ever take organic chemistry, you're going to use different solvents. Carbon tetrachloride, maybe one of them, but we'll have CCl. So C for carbon, Cl for the chlorine again. But in this case, we've got 4 of those chlorines. So we just want to include that. And then the last 2 slides here, just kind of mentioning it so we're aware, but we won't do too much with this until we actually talk about like acids specifically. But acids are going to be substances, if you look here, so this just comes from the textbook, that's why there's just so much text. But acids are just going to be substances that when we dissolve them in water, they increase the hydrogen ion concentration. And if we think about what a hydrogen ion is, H+, hydrogen is almost always just hydrogen 1. So in that case, it's going to be 1 proton, but then nothing else in that nucleus, so we'll have no neutrons. And then we'll just have 1 electron on the outside. But in this case, since it's hydrogen plus, we've lost that electron. So sometimes they're called hydrogen ions. Other times they're just referred to as protons, but they're the exact same thing. So acids are going to increase the hydrogen ion concentration, or they're going to increase the proton concentration. And with it, we again, binary acid. So we're going to have the acidic piece, we're going to have that hydrogen. just with one other element. So you can see in this case, fluorine, chlorine, bromine, iodine, sulfur. So with these acids, they're still covalent. We still just have nonmetals there. So they're still going to be sharing electrons in the bond between hydrogen and whatever the other atom is. But we have a slightly different naming system for it. Typically, we're going to be using the name of the acid. So if you look here, we in each case have HF, HF, and then the same thing for the other ones. But with the name of the gas, we've got a little G next to it. That's referring to, we have that substance in the gas phase. And in that case, we would name it sort of similar to the ionic, or not the ionic, the covalent compounds we were just looking at, where we would keep that element, keep the first element the same, so just hydrogen. But then with these ones, it's a little bit different in the sense that we don't have a prefix with it for the second element. So it's just hydrogen fluoride or hydrogen iodide, hydrogen sulfide, whatever it may be. But like I was saying, we're typically going to be working with these as solutions. And that's what the AQ represents. So AQ just stands for aqueous. So we took that substance and dissolved it in water. So this would be a solution of hydrofluoric acid, hydrochloric acid. So when that's the case, we're going to kind of drop the ending of both of these elements and just sort of mash them together. So we have hydro and then fluoro. But then the ending here is just going to become IC acid. So hydrofluoric acid, hydrochloric acid, hydrobromic, hydroiodic, hydrosulfuric acid. And then just note, we'll talk about this also when we're looking at chemical reactions and things like that, because the state of matter can affect a reaction. But AQ is going to be a solution, so it's going to be in a liquid form. But AQ is going to be different than liquid because what AQ represents is taking that substance and dissolving in water. Whereas if we just had an L, that means we actually took that substance and put it into the liquid phase. So if it was a solid, we melted it. If it was a gas, we condensed it. But the liquid is going to be that pure substance just as a liquid, whereas AQ is going to represent whatever that substance is dissolved in water. So typically when we're working with some of these acids, so we'll work with hydrofluoric, very rarely, if ever, in our lab. I think in Breaking Bad, they use that as like if you've ever seen it, they use that to essentially just like melt a body. I don't think he'd ever actually, I think that would be a poor choice for it in reality. But we will work with hydrochloric acid, hydrobromic at some points, hydrosulfuric acid. So we'll work with some of these. And when we do that, just because they are acids, we'll always make sure have our gloves on, our eyewear. But with it, we'll always have it kind of in the solution. So with those, even when they're pretty high concentrations, they're still going to be very dangerous, but it's going to be mostly water mixed with the acid. Whereas if we just had liquid, it would just be that pure substance by itself. But even at low concentrations, these can be harmful. So we're always going to, while working in the lab, make sure that we're handling them with care, because even at low concentrations, they can damage you if you get them on your skin. Of course, if you get them in your eyes, that's going to be extremely problematic. But we'll always make sure to have proper safety going on. And then the last one, kind of similar, oxyacids. So as the name would suggest, it's going to be an acid. So we're still going to have that hydrogen piece. So if you look at all these formulas, they start with the H. That's not always the case with acids. But if you see it like this, it's a pretty good indicator that it probably is an acid. But as oxyacid would suggest, we're going to have that combined with oxygen. And then there's going to be one other piece with it. So you can see hydrogen, oxygen with phosphorus or sulfur, carbon, chlorine, nitrogen, whatever it may be. In this case, we've got the hydrogen in two different spots, and we'll kind of see why that is when we get to the structures of substances like acetate, and when we talk about acids as well. But with these oxyacids, they're still going to be covalent substances, so we're still going to have covalent bonds holding those different atoms together. But when we name these substances, when we name these oxyacids, we're not going to include hydrogen in the name at all. What we're simply going to do is change the ending of the anion. So you can see we've got SO3, CO3, whatever it may be. We're going to change the ending of that. And if it's an ATE ending, so you can see sulfate becomes sulfuric, perchlorate becomes perchloric, carbonate, carbonic, acetate, acetic, nitrate, nitric. So if it's an ATE ending, we're going to change that ending to IC and then just add acid on the end. And then if it's an ITE ending, nitrite, sulfite, very similar idea. It's just instead of IC, we're going to have the OUS ending. So nitrous acid, sulfurous acid. If we had chlorite, then it'd be chlorous acid. But with it, we're gonna sometimes use some of these. So phosphoric, we'll see. Sulfuric, we'll see a whole bunch. Carbonic acid, not too often. I'm trying to think. Nitric acid we'll use. That's a real nasty one. And then acetic acid is actually just the substance that gives vinegar its characteristic smell. So it's a very weak acid. But if you do have it in the glacial form, which is essentially just a whole bunch of it in solution, that one can be dangerous as well. But in vinegar, of course, not really anything to worry about there. But with this will be the end of the video. So if you do have any questions related to those different types of compounds, whether it's ionic or covalent, naming, formula, whatever it may be, please reach out to me. Please reach out to me and we can meet during office hours. And then remember, with all this stuff, there is different practice on Canvas, along with the answer keys. So there's different practice for the individual topics, at least most of the individual topics. But then there's a general chapter review for each of them. And the textbook has a bunch of practice too if you're looking for it.